This is a very quick introduction into containers. If you are already familiar with containers, feel free to skip this session. But if you are new to containers and want to know how containers function, within few minutes, I will give an introduction into containers and the essentials that you want to know to continue the subsequent labs. So what's the difference between virtual machines and containers? They both need to have a server to run. They both need to have a host operating system. And in the case of virtual machines, you have this thing called a hypervisor. A hypervisor abstracts the underlying hardware, and on top of this hypervisor, you can start virtual machines. So these virtual machines could be, let's say, Windows 2008 servers or Windows 2016 servers, Linux servers, and so on. The challenge with the virtual machines is that the shareable resources are not properly shared. For instance, imagine that you are running the same operating system. It could be, let's say, Windows 2016 servers. 99% of the time, the content in these binaries are going to be the same. And same for the libraries and binaries. Imagine that you want to have .NET Framework installed on all these virtual machines. You are going to install it in each virtual machines, and you are going to waste storage. Because although the binaries are same, you are not going to share it across the virtual machines. It also applies for processors running inside these virtual machines. For example, if you have a virus scanner, or if you have a firewall, a process that consumes memory and CPU, you repeat the same process that gives the same service across the virtual machines. And then result of that one is that you allocate more resources than what is actually needed. So there's a resource wastage when you select virtual machines. In the case of containers, you have this concept called immutable images. For example, let's say you want to have Windows 2016 server with .NET Framework installed. So you can have that OS image 1 with Windows 2016 server and common libraries installed, and you create an image out of it. And when you want to run applications on that, you simply start the containers, and they can share that common resources, all the libraries, the operating system content. What it means is that the containers are lightweight. They don't need to go through a very complex boot process like virtual machines. Some OS processors are already started for them as part of the host operating system. And when they run, they don't need to create a very complex process structure, and they start very quickly. You can stop them very quickly. These containers are also isolated from the other containers. For example, the address space of container 1 over here is different from the address space of container 2. So for example, if a process is crashing on container 1, it does not affect what is happening on the container 2. They all have their individual file systems. They all have their individual process trees. So there's no way that the container 2 can interfere with what is happening with container 1. So in that case, you get some kind of an isolation and the same features like a virtual machine. The beauty of this one is that you end up utilizing the hardware resources better than virtual machines. So effectively, you increase the application packing density. So instead of running 2 virtual machines in a given hardware, you now can run 6 applications on a server. Because at the end of the day, what we care is what our applications do. We don't care what the operating system is doing, right? That's just a service that we use to provide to run our applications. And the next thing we need to learn is about Docker images and layers. So imagine that you have 2 applications that are containerized. You have this concept called Docker images and the layers. So Docker image comprises of multiple layers. So the application 1 may be depending on the first operating system, which is about 10 gigabyte. You may then decide to patch this operating system, which will add another layer of about, let's say, 2 GB. If application 1 is a .NET framework, you may decide to install .NET framework in layer 3, and layer 4 you may finally end up installing the application. So you can find that there's about 12 GB of layers that provides basic functionalities. So if your application 2 is a Java application, it can start depending on the layer 2, which is a patch version of the operating system, and then install Java framework on top of that, and then finally the application. So you have this concept called shared layers, which effectively allows you to share some binaries. And beauty of this one is that you don't waste a lot of storage. And if you are creating some CI/CD pipelines, or if you plan to move your containers from one container host to another, they move very fast because the existing layers are not downloaded. So for example, if you have these base layers already on existing the container host, when application 2 comes, it's only going to download the layers that it needs. So here you have like 2 applications, application 1 and application 2. Imagine that they are ASP.NET latest applications. And at some point in time, let's say you want to patch the ASP.NET version. So here I have given some random number called version 10. And if you want to upgrade, you can easily upgrade this one by getting the latest version or the latest layers of this ASP.NET. Of course, you need to run a test after doing this upgrade like any other application. But the upgrade process itself is very seamless and easy to do. And when the Windows Server operating system upgrade comes into picture, you can also do that very easily. You just upgrade, you get the latest layers of that Windows Server. And provided that you have the API compatibility, the upgrade process is very easy. The ASP.NET latest, because it depends on the Windows Server latest version, will continue to function, and my application will continue to function very easily. So there's no need of going there and then doing the patching manually by remote logging into these machines. There are a few components in container environments. The first one is the OS. You need to have an operating system that supports containers. You cannot run containers on, for example, legacy Windows servers or legacy Linux instances. And then there's a component called Docker Engine. So this is what exposes the API to interact with containers. So when you interact with what you call the Docker Engine, what you do is you effectively invoke these APIs, either to some kind of a Docker client or through some kind of a tooling to stop containers or to get images. So that's the Docker Engine. It runs on top of an operating system that supports containers. Then you have the containers itself. So this is what the container engine manages. So it starts, you can stop them, you can get container images, you can inspect what is happening in the container. So these are the running containers or the stop containers. Then you have the other component called the Docker client. So this is what you execute when you call things like Docker run, Docker images. So the Docker client is the one that invoke Docker Engine APIs, usually on the same machine it runs. You can also connect Docker Engine running remotely to a Docker client. So hopefully you get an idea around how Docker functions. In the next section, what we are going to learn about is orchestration engines that allows to orchestrate multiple containers on different environments.